Hi, my name is Matthew Fisher. This is ECE 561 at North Carolina State University. I'm demonstrating Challenge 2, and let us begin. Hi, my name is Matthew Fisher at North Carolina State University. This is course ECE 561, section 001. And I'll be demonstrating Challenge Assignment 2, which is to emulate a home monitoring system with a watchdog timer. First, let's begin by showing the requirements of the device. First, the embedded device essentially should have a doorbell press, which lasts roughly 2 seconds in time. Our alarm activation and deactivation button should exist, and when activated, the alarm should show a red LED state. When deactivated, it should show a green LED state. And also during the activation state, should a sound be picked up by microphone. The alarm type sound should occur through a piezo buzzer. Should a glass break, which is essentially a light sensor picking up a bright light, be picked up, it should essentially preempt or take highest priority of either the doorbell or the alarm system sounding off itself. Let's first begin by showing the programming of the device. Here's the MSU432 with the booster pack and its current ready LED state. The device is plugged into the laptop, and here is the IDE. I'm going to begin by programming the device. It is now waiting to be ran. I'm then going to stop the device so that it can be unplugged and replugged to show that its current program state can run in free run mode. The device is starting up in green state, ready state, as specified within documentation. First, a door press. Since it is time-based, I'm going to lightly attempt to try to press both of the doorbell button and my mouse pad at the same time so that I can time the device. So I'm going to bring up a screen timer and then press both at the same time. There we go. And there it is, roughly 2 seconds as required within documentation. Next, I'm going to show that the alarm can be activated and deactivated. So this is the deactivation button, and it can be activated and deactivated many times. It doesn't affect it. There is button debouncing going on. So if it's in the activation state, you can arm and disarm the device, or not really arm and disarm, but you can set the alarm off, and this can then be stopped using the deactivation mode. And when I deactivate, the alarm is still not running, so the alarm can be deactivated as specified. If the alarm is activated and the alarm is going off, the doorbell will not cause it to stop or interrupt. And I'm pressing the doorbell button and it is not causing the alarm to stop, but if I deactivate it, it will. Next, I'm going to demonstrate the alarm going off, but the light sensor picks up a bright light, which will cause a preemption of all modes within the hierarchy of priority. So I'm going to arm it, and I'm going to get a flashlight, and then I'm going to set the alarm off and then cause the device to go into a fire alarm mode, which will require hardware resets as specified in documentation. And this runs indefinitely as required within the report requirements. And when it's put back in, the device initializes in the ready state and it's ready to go again as specified. And this concludes the hardware demonstration requirements for Challenge 2 at ECE 561 at North Carolina State University. Thank you. Hi, my name is Matthew Fisher. This is ECE 561, section 001, and this is North Carolina State University. I'm going to be demonstrating Challenge 2 and explain the code process for how to implement the challenge for a home monitoring system with a watchdog timer. So let's begin. I'm going to be discussing 4 main topics at first. The first topic is an IDE-related analysis feature, and that analysis feature which I'm going to be showing is called Energy Trace. So to begin Energy Trace, I need to go ahead and compile the program. And next I'm going to be going to Tools, Energy Trace. And Energy Trace pops up here in a small window. And next I'm going to be pushing play and run the software. And then it analyzes my average power of the MSP432 as well as the booster pack in its current state. And this runs for about a minute. I've got it set for a minute. It's actually 60 seconds. And it'll do some analysis features for power draw. And this concludes my analysis feature for the IDE. Next, I'm going to be showing the Optimizer Assistant. So the Optimizer Assistant is under View, Optimizer Assistant. I have it here at the window. And you can see here I've already ran it. This does take quite a bit of time to run. So now I'm going to be essentially showing you that Optimization Level 1 does actually have the least amount of memory required for the code to implement correctly. And this is what I have selected for optimization within Optimization Assistant. And that's my IDE-related optimization feature. Next is my implementation-related analysis technique. The implementation-related analysis technique which I'm going to be using is called a count event. So if you set a breakpoint, the pointer essentially hits this breakpoint, it's now waiting. You can configure a count event essentially to reset on run. So then I'm going to show that its current value is some large value, and I'm going to run it. And it now has hit the breakpoint, and it shows a count value of 135 cycles. And that's how long it took to go from the bottom and from low power mode and essentially wake back up from low power mode with a timer that happens every quarter of a second, and then come back up to the breakpoint itself. So that's my implementation-related analysis technique. And the fourth topic is implementation-related optimization technique. The implementation-related optimization technique which I'm going to show is involving the topic of bit fields and unsigned integer sizes. So that was located within my buzzer.h file. I have 2 structs. These structs are utilizing unsigned integers of 8-bit size. These are used anytime I need a value that is not negative. I use an unsigned int and specify 8 bits explicitly. And this is done simply because it saves memory. If I don't need an integer size of 16 bits, I don't use the integer size unless it's needed. So I specify within my code 8 bits unless the size requirement specifies or needs more. That's one topic of optimization. The next is called a bit field. These little flags or numbers here are called bit fields for structs. You can essentially tell the compiler that even though this is an 8-bit unsigned integer, you specify or only desire 1 bit of that 8-bit type, and it will optimize for only using that particular bit, and is able to combine all of these into a single unsigned integer of 8 bits in size. And so the maximum particular size for the struct is actually the maximum of whatever bit field requirement you have within that struct. I'm using that for my flags as well as my pattern controller struct. And this is a C++ feature which is allowable in C as well. Next I'm going to be demonstrating the advice window. So in the device window I have only advice recommendations for power. My power advice recommendations are for either using DMA or I have some global variables in particular functions. However, these recommendations are within files I did not write. I did not create AES286 or PMAP or flash.c. These are all within the driver lib, and we are not required to optimize within driver lib, as that's an API that's given by TI directly. Next, I'm going to be demonstrating the code. the major features which I want to demonstrate are the ADC, the initialization of the I2C protocol here, the sensor, and finally the normal power mode configuration. I will not be covering timers, watchdog, or button debouncing because those are implementation features which were done in a previous challenge called Challenge 1, and they've already been covered and given for implementation use only, and they will be reviewed in another section of the project. So let's begin. First is the ADC. The ADC is configured to be selected for its functionality. It's essentially a GPIO select the analog input, and I'm using default parameters from page 12 and page 113 of the datasheet to do so. So these documentations require essentially the direction to be an input and the output to be essentially just low. And this is just initializing the ADC itself for the MSP432. So I'm selecting the ADC and then setting the parameters accordingly. Next, I'm configuring the ADC. I'm going to be very clear that this is example code given within the driver lib, page 12 and 13 of the documentation. I did not write the majority of this part of the software. I did modify it slightly to fit the needs as required. I did manually register the handler from a void pointer to the ADC to make sure it always ensures functionality no matter who actually runs the code. And that handler is down here in the bottom. Excuse me, sorry. Next, I actually modified it so that channel A10 is used for the microphone. So it's very clear that the microphone is on port 4, pin 3, and this port requires channel 10 in order to function correctly. So as stated here, port 4, pin 3, which is the microphone itself, does have A10 as a selectable function, and it does require 1-1 for the select bits. And that's essentially what I'm doing to select channel A10 to make sure it's functioning as intended. And I'll also be clear this, I'm setting the resolution for the ADC to 10-bit. You could actually use 14-bit as it is a 14-bit ADC, but you get values that are much less accurate, much larger in value. So 10-bit was enough for me to be able to have values that made more sense and were not quite as noise prominent within the software in general when you're actually registering data from the ADC. So next, this is going to be essentially concluding the initialization and configuration of the ADC. Next is going to be essentially the buzzer as well as the I2C protocol. So the buzzer is just simply being set up as an output from a timer A0. So timer A0 is using PWM to go to this particular buzzer, and that's what's creating the sound. And it's in a nominal range of around 2 kilohertz for functionality. And timer A0.CCR4 is used to output to the buzzer as specified within page 101 of the datasheet, which I believe I have here. And this is port 2, pin 7. So simply just go to the chart and I scroll down to port 2, pin 7 for the ADC. There it is. Port 2, pin 7. You then can use timer 0, CCR4, and essentially you can select it here. So it's given in this particular area right there. And that's what I'm essentially using. So that concludes the initialization of the buzzer. And like I said, I2C is what I really want to hit next. So I'm going to go to this particular location. Here is the initialization for EUSCI B1 base. This is a module within timer which is configured for I2C protocols. This has an initialization struct, which actually is not something I created.
TI owns responsibility for this code. I did not create the sensor I2C or I2C code itself, or the sensor code. TI owns responsibility for this software. You initialize the ports, and then you have the ability to then read or write code as needed to the particular device over I2C protocol, which is a serial communication protocol. And that's the sensor itself. And next, and essentially last, is the light sensor. It has a slave address of hex 44. This is required by the device datasheet to work correctly. So its slave address has to be set to this for it to work. And then you have to write to the configuration address is 0x01, a default configuration parameter of 100 or 101. And again, these are all specification flags here that set the features needed within the light sensor, because the light sensor communicates over I2C. And last is normal power mode. Normal power mode is one of the features between low power mode and low power mode. This is 24 megahertz for DCO and then 32 kilohertz for reference 0, or ref O clock, or ref low oscillator. MS and HS clocks are using DCO, and then A clock is set to ref 0 for functionality for my timing particular needs. Low power mode is LMP 0, as mentioned earlier. I am utilizing low power modes, and I'm using vCore 0 to make sure it's within that particular state, and I have to set ref 0 to 120 kilohertz for that to work correctly, as stated whenever within the datasheet here. So for sleeping clock, it must be less than 120 kilohertz for it to actually be in a sleep mode for LPM 0. And that's exactly what I'm utilizing within this configuration. And that is shown here within the lowest priority of the particular program itself. And that concludes my, essentially, explanation for the program. The last thing I'm going to discuss are the biggest challenges that I encountered for this particular software challenge. The biggest challenge would actually be the essential initialization and read up on low power mode. And the next would be I2C. So between I2C and low power mode, both of those are features which were extremely long and difficult to understand and read to be able to implement correctly. Low power mode is not something you can just add into your code, I believe. This is something that has to be designed with in mind from the very beginning, and it requires quite a bit of effort to be able to understand what each mode needs in order to work correctly. It required a lot of reading and understanding in terms of how do you wake something up from a low power mode, and how do you structure your code so that it can actually utilize it correctly, because you do actually stop the program counter. It does not work whenever it's in low power mode. Interrupts wake it from low power mode, so you can actually interrupt or continue running code as needed. And essentially that concludes my explanation for Challenge 2. I want to thank you very much for your time, and this will be the end of my video.